you're hoping on more on particle motion, yay, we can do it. There's more on particle motion. So this is Daily Lessons, page 136. So the graph below represents the velocity v of t. That's fantastic, but I wish they would have made this bigger, so label it. V of t, which is measured in meters per second, important, don't change that somewhere along the way, of the particle moving along the x-axis. So again, the particle is not moving up and down and whatever, it is moving right and is moving left, and sometimes it stops. So, at what values of t does the particle have no acceleration? So you have to think about this. Acceleration, okay, how are they connected? It's position, velocity, acceleration. Take the derivative of position, you get velocity, take the derivative of velocity, you get acceleration. So if I want no acceleration, I want a of t to be equal to 0. Is this t? Yeah. A of t to be equal to 0, which is the same thing as v prime of t being equal to 0. Okay, so when I have v prime of t being equal to 0, so on what values of t does the particle have no acceleration on the interval from 0 to 10? I would say as a of t equals 0 when v prime of t equals 0 and v of t, this is the graph that we're given. We're not given the graph of v prime. We're given the graph of v of t. So I need, and v of t has a horizontal tangent. We're going back to what's going on to v of t. Has a horizontal tangent. I'm justifying before I get there. And v of t has a horizontal tangent. The particle has no acceleration. I'm going up here now. And if you look here, this is kind of a weird one, but it has no acceleration. The derivative does not exist here. So you could have some argument for, well, the derivative doesn't exist, therefore there's no acceleration. But at this point, I'm going to talk about zero acceleration. So not there, because derivative does not exist. Acceleration does not exist there, which seems kind of weird when you're talking about a particle. But actually, here is where the horizontal tangent is going to be. It's going to be from 3 to 6. So on the interval, three to 6. So again, the derivative or acceleration does not exist at 1, at 3, at 6, and at 8. But it does equal 0 from 3 to 6. Okay, express this as a piecewise function. You will not have to make your own piecewise functions, but you could on this one because you're smart. Okay, so a of t is equal to, it's not asking me to come up with the velocity piecewise function. It's asking me to come up with the acceleration piecewise function. So really, all I care about is the derivative of v of t. Derivative, also known as slope of the tangent. I can see that I have a slope right here, I have a slope right here, slope right here, slope right here. They're all straight lines, so the slope of the tangent is just going to be the slope. The same thing that you learned a long time ago in Algebra 1, y2 minus y1 over x2 minus x1, and these ones I'm going to go through. If you count that out, rise over run, y2 minus y1 over x2 minus x1, change y over change in x, whatever that is, you're going to find out that this has a slope right here of 3. And then over here we have a slope of negative 3, from there to there. Then I have a slope of 0. Then I have another slope of, hey, this is exciting, 3. And just to mix things up, the last slope is going to be negative 3 over 2. So, in my piecewise function, my value for acceleration, it's not even a function, so it's not even that crazy and exciting. It's going to be 3, then negative 3, then 0, then 3, negative 3 over 2. Super boring piecewise function, but, you know, we'll take it. But I need to know when that happens. So it's only 3 from 0 is less than t is less than 1. And again, I'm not including anything because the derivative doesn't exist at 1. And then I'm going to go from 1 to 3, because I went 1 to 3, then 3 to 6. And then the last one is going to be from, oh wait, no, not quite the last one. 3 to 6, 6 to, I believe that's 8. Yep, 6 to 8. And then the last one is going to be 8 to 10. Okay, for what values is the particle moving to the right? Think about this. When does a particle move to the right? Particle moves to the right only when velocity is positive. Okay, so when velocity is positive. To the left is when velocity is negative. I'm given the graph of velocity. I know it because I labeled it really big. So if velocity is greater than 0, I'm just looking when it's positive. So here and then. So the particle moves to the right on the intervals 0 to 2 and 7 to 10. As v of t is greater than 0. Same thing on the left. Particle moves to the left. I'm going to skip that part. Left on the intervals. I'm only looking where it's negative. So actually it's just on one interval from 2 to 7. As v of t is less than 0. Okay, last one. Average acceleration. Average. As soon as you see average rate of change, average anything, you should be thinking slope of the secant. It's not nearly as good when I have you to not interact with, but you know. Average acceleration is just going to be the slope of the secant. But it's the slope of the secant of velocity. So when you're talking about average acceleration, you should be thinking v of 8 minus v of 1 over 8 minus 1. I can get these values from the graph. At v of 8, I see a value of 3. V of 1, I see a value of 3. Boring. 3 minus 3 over 8 minus 1. 0 over 7. This one, you have to have units because I was given units to start out with. Velocity was given in meters per second. So right over here. So this one, 3 minus 3 would be 3 meters per second minus 3 meters per second. I get 0 meters per second. Over 8 minus 1. This was dealing with seconds. So meters per second, or you could say meters per second squared.